So, good afternoon, everyone. Today we are here to present on a meet regarding the second tutorial session in NPTEL course, Chemical Engineering Thermodynamics. So, we will discuss few example problems regarding uh, different thermodynamic processes involved in nature. So, whatever we have discussed in the week two videos, it is all about the volume expansivity, isothermal compressibility, these things, the equation of state, and the ideal gas behavior, and what is the work or delta U, change in internal energy, or heat given out or heat taken by the system, and also change in enthalpy of the system. How does it change with the different process? And also, if it is reversible process or if it is irreversible process, how will values of the changes in energies will change? So I would like to share my screen. So firstly, I would like to introduce myself. I'm Namrata Kulkarni, a PML scholar from IIT Madras. So uh, here we can discuss that ideal gas behavior is a very approximative way of assuming fluids. So this behavior is possible only at very low pressures and high temperatures, where we can assume that interparticle distance is very high. So there are no molecular interactions. So that's why uh, the change in internal energy is only dependent on the temperature, and there are no forces in between the molecules. That is when we assume that it is an ideal gas. And for this condition, this ideal gas behavior PV is equal to nRT is followed, where N is the number of moles. If we assume that PV is equal to RT, then it can be the specific volume, that is volume per mole. Okay, then it is expressed that way. Right, yeah. So V is equal to RT. Here, this is specific volume. Okay. So this is the condition. So now a particular thermodynamics process, for example, if we take the PV space, assume that like first point is somewhere here, P1 and B1, and some T1 are related by this relation. Okay, and we are going to some other point where it is P2 and V2. So we can go in any way, okay? Either like this, or we can go like this and like this. Where here it is like the volume is constant along this path, and along this path, the pressure is constant. So that way, we define different processes that can happen when changing from one state to another state. Firstly, the isothermal state is defined by when T is constant. Okay. So, and isobaric when P is constant, isochoric when V is constant. And lastly, adiabatic process where we assume the heat loss, the Q is zero here. Okay. So to find the change in internal energy, work, heat, and delta H, so here we can see that we have two different variables, CV and CP. Okay, so the definitions are this is heat capacities. Okay, specific heat capacities where CV is defined as dou U by dou T. Okay. And CP is defined as dou U by dou T. Sorry. Dou H. Okay. Dou H by dou T. Constant. So, considering that we have this situation where delta U is integral of CVDT. And same for the enthalpy condition in different processes. But in the isothermal case, if we consider the T is constant, so delta T is constant. So that's we have here 0 and 0. So generally, this is the in the integral CV can be a function of E and T. Okay, so mostly it's a function of temperature only. Okay, so while integrating, we can consider the temperature which is here. So integration based on that. And for the other processes also, if we see, I'll come from one to one. Okay. In the above thing, I have forgot to say that all these processes follow a same trend. That is, PV power delta is constant. Just give me a minute. Yeah. So PV power delta is constant. Here in different processes, in the isothermal case, PV power 0. So in adiabatic process, we have PV power gamma is constant, where we define gamma is equal to Cp by Cv. Okay. And one more thing is we have Cp minus Cv is equal to R. Okay. So when we have one of them, we can find out gamma and also Cv, right? If we have Cp, we can find Cv. And based on that, we can find gamma also. So we need to have at least one of them so that we can find all the different measures in an adiabatic process. So coming to the first process, the isothermal, we have delta T is 0. That's why we have delta U is equal to delta H is equal to 0. Now we have the first law, which is delta U is equal to Q plus W. Okay. this is 0, it implies, and this W is generally defined as minus PdV. So we have PdV is equal to Q. Now we define this P can be expressed as like if we know pressure, we can do that. Or else, since this is for an ideal gas, we have PV is equal to RT, right? So P is equal to RT by V. And we have now Q is equal to, so this is actually um, dq minus PdV. Okay, because I'm talking about only infinitesimal difference where I define this PdV. So that's why the Q is also infinitesimal difference only. Okay, right? dq. So dq is equal to PdV is equal to RT by V dV. And on integration, we have this complete Q is equal to RT ln V1 by V2. Okay, this is what I have shown in this uh, thing. Right. And this way, as explained in the videos, you can write for different processes, right? Isochoric and adiabatic, and everything is explained in the videos for you. So this I have explained a small one of the process I have explained you here. So coming to the few examples, I'll show you. Okay, given here we have we take granted that Cp minus Cv is equal to R, but how is it? We can derive it actually, right? So we have Cv is equal to dou U by dou T at constant V. And Cp is equal to dou U by dou, sorry, dou H. Dou H by dou T at constant P. So these are defined like this. And you know, yeah. So this H derivation, this is like H is an derived. Give me 1 minute. So the recording of this is generally uploaded on YouTube. And I think this should be shared by the NPTEL team. Okay. I am uploading these videos on YouTube, which are uh, I'll be filling the form. The spreadsheet is there. Either the spreadsheet should be shared with you guys, or you should be informed in the normal portal is there, right there. Okay. Or else I can give you the YouTube account name. Okay. It is The name is Namrata Kulkarni only. With my name only, there is a YouTube channel. Okay. I'll send the link, but here I can. Like this has to be uploaded still yet, okay? I can't send you here. It has to be uploaded. I can send you the channel link. Okay, 1 minute. So due to network issues, all the process are slow in my system. So please be patient. So yeah, as I was explaining, H is equal to U plus PV. This is a derived quantity actually. Most of specifically understandable quantity here. So we can express this as so here we have dH is equal to CPdt. If we do this equal to du plus d of PV. Okay, and we also have here du is equal to CV dt. Yeah. Actually, this video is for you only, actually for live participants only. So you can interrupt me, you can ask any doubts you have, okay? So this is for you people only. This is just recorded for those who could not uh, attend and could not make out time for this, okay? So you can ask any doubts if you have. From the assignments also you can ask. From the course also, if you don't understand, you can ask. Since this is the beginning of the course, maybe you might not have so many doubts, but later you will be having few doubts. Okay. So you can ask questions, Mahesh. Okay. Yeah. Thank you. So I'm just going through few example problems so that you get the concept better and you can solve problems easily. That's all. And you get some practice also. So here, this is defined for ideal gas only, okay? So that's why we have PV is equal to RT, right? So the D of PV will be RTT. So that's how DH is given as CPDT is equal to CVDT plus RDT. And that's how we get Cp is equal to Cv plus R by cancelling out the thing. Okay. Fine. Now, coming to the second question, we have a compressor which compresses to 3 times the feed pressure. Okay. We have a compressor, inlet pressure is P1 and outlet pressure is P2. And P2 is equal to 3 times the P1 at 300 Kelvin. So T1 is equal to 300 Kelvin. It is assumed, so enters a compressor at 300 Kelvin. Okay. It is assumed that there is no heat lost. So Q is equal to 0 at all already says that it is an adiabatic process. Okay, so assuming air to be an ideal gas, gamma is equal to 7/5. What is the outlet temperature? Right, generally adiabatic process, we have PV power gamma is equal to constant. Okay, now gamma is already given 7/5. We have pressure and temperature. So then we can see this can be changed in many directions. Here, this is an ideal gas, right? So we have PV is equal to RT. So we can be expressed as RT by P. And the only proportionality things we take here, so P is into T by P, our gamma is equal to some constant. So I say P power 1 minus gamma, T power gamma is equal to constant, leading to P1 minus gamma by gamma into T is equal to constant, right? So if I take T2, okay, here P1 into 1 minus gamma by gamma T1 is equal to P2 1 minus gamma by gamma T2. So T2 is given by T1 into P1 by P2 or 1 minus gamma by gamma. And this gives us T2 is equal to T1, which is 300 Kelvin into P1 by P2, which is 1 by 3 power 1 minus gamma is okay minus 2 by 5 by gamma, which is 7 by 5. So this is 300 into 3 power 2 by 7. Okay, this is how you can make changes into the same thing and find relations between P and T and V and T and P and V like this. Okay, different combinations can be arranged. Okay. Now, an ideal gas undergoes expansion according to the process PV power 0.5 is equal to constant. So the temperature of the gas during the expansion process increases or decreases, that you have to say. So here it is mentioned expansion. So when you expand something, it means the pressure is decreased, right? So we say P1 V1 power 0.5 is equal to P2 V2 power 0.5. We are talking about the temperature, so we want to convert it to P into T, okay? Now we have PV is equal to RT. So V is expressed as RT by P. So that's how you will get P1 power 0.5 and T power 0.5 is equal to P2 power 0.5 into T2 power 0.5. Okay. So if this is almost same as P1 T1 is equal to constant. So if P is decreased, this should increase for remaining constant. So we have this should increase. Okay. Now, in this question, I wanted to include all different processes we have been talking about. Okay. So an ideal gas undergoes the following sequence of mechanically reversible processes in a closed system. From the initial state of 71 degrees and 1 bar is compressed adiabatically to 150 degrees. So it shows me limited time. I hope it doesn't end. If it ends, we will rejoin the video, okay? Hmm. So these three sequences are followed. Now we have to calculate work Q, delta U and delta H. So the first process is an adiabatic process and that is the compression process. So adiabatic, it shows Q is equal to 0 and compression means the pressure is higher. Okay, P2 is greater than P1. This is the thing. If we see this process, if we assume P versus V, assume some pressure and volume here, that's 70 and 1 bar. Okay, this is some temperature given. Okay, some V1 volume is there. The next one, the P2 is greater than P1. Okay, and since we generally know PV power gamma is constant and pressure increases, so the volume also decreases. So that's how the final point should be somewhere here. Okay, and then cool from 150 to 70 at constant pressure. Okay, we'll go slowly, okay, coming from one step to step two, okay. The step one is this. Here, Q is equal to 0, delta U is equal to Q plus W, Q is 0, and yeah, we have been given CV here, right? CV is equal to 3 by 2 R. So CP should be CP minus CV is equal to R, right? CV plus R equal to 1 plus 3 by 2 is 5 by 2 R. It implies gamma is equal to CP by CV is equal to 5 by 3. Right? Now we have a relation between pressure and temperature. So we have PV power gamma is constant and we have derived so many times till now. That is P T by P power gamma is constant. So we have P1, P2 by P1 is equal to T1 by T2 power gamma by gamma minus 1. Okay, this relation. So we have already this. Okay, P2 is equal to P1 into T1 by T2 power gamma by gamma minus 1. So which gives it is 1 bar and this here the temperature should be in kelvins. Okay, so 150 degrees Celsius plus 273.15 and this is 70 plus 273.15 power gamma by gamma minus 1. We get it as 2.5, right? Then on solving I get 689 bar. As predicted, this So I'm resuming the session here. So as predicted, we have got P2 greater than P1. So we are moving from state 1 to state 2. Now we already have Q is equal to 0 here, and as we know that delta U equal to Q plus W, okay, is equal to W is equal to delta U is given by CV into delta T. Since we know delta T already, here CV is 3 by 2 into 8.314. This is all in joule per mole Kelvin. Okay. Into Kelvin, which is 150 minus 70. Here, whatever the temperature difference is in Celsius or Kelvin, it will be same. Okay, these are the difference will be same when it comes to the Celsius and Kelvin. And for the Fahrenheit and Rankine, also they are linearly connected, right? So the difference will be same. So this is what you take, and now we have delta U is equal to 998 joules here. So this gives us positive work. It implies some work has been done on the system, right? And similarly, delta H is equal to Cp dt, Cp delta T. Here we know Cp is Cv plus R. Okay, so which is 5 by 2 R we had. So on calculating that, I will get 1663 joules here. Okay, so in this process 1, I have Q is equal to 0, delta U is equal to 998 joules equals to work. Okay, both are same here. And delta H is equal to 1663 joules. And coming to the step 2, this is cooled from 150 to 70 at constant pressure. Okay. Now, we define again in the second process. At constant pressure. So therefore, Q is equal to delta H. Okay. And is equal to Cp delta T. And again, the delta U is equal to Cv delta T. But since here it is the reverse of the process, we are going from 150 to 70, so delta T is negative here, right? So delta U is negative, which is again minus 998 joules. Okay, and this Cp delta T is again the negative of this minus 1663 joules. Okay, U is equal to minus 1663 is equal to delta H, and delta U is equal to minus 998. And coming to the work, it's delta U minus Q, right? Which gives us 665 joules, and it is also positive work. Coming to the step 3, we have expanded isothermally to its original state. So this is expansion process. Okay. So we can say it is more like a this this, because when we did first time, the pressure has increased and volume decreased. Okay. And at constant pressures, temperature is decreased. So when we have this PV is equal to RT, so pressure is constant. When temperature is decreased, it means volume is decreased. So this is the second process. And finally, it's brought to the original state by expansion. So expansion means the pressure is decreased, right? So that's why the expansion process is there. Or you can also understand it as volume is expanded, right? So this is an expansion process. And this is done isothermally. So here delta T is 0, here it was Q is 0, and here delta P is 0. Now What coming to the step 3, delta T is 0. So delta U is equal to delta H is 0. This is an ideal gas. So Q is equal to minus W. We have dW is equal to minus PdV. Right. And this P, I can express it as minus RT dV by V using the ideal gas expression. So that's how we get minus nRT ln V1 by V2. So here it's not V1 by V2, it's actually if I say this is 0.1, this 0.2, 0.3. Okay, so this is initial stage, which is V3, and this is final stage. So this is the final stage. It becomes V1. And this is initial stage, right? Which is V3. So we generally by integration we say V1 to V2. So that's why I integrated this and wrote V1 by V2. But it's like V initial to V final. Okay. So when I have done this on integration and application on substituting the values, we get minus 1495 joule. So this is negative work. So we consider here step 3. Q equal to 1495 equal to minus W and delta U is equal to delta H is equal to 0. So coming to the entire process, if we sum up all the 3 processes, we get Q is equal to minus 168 joules and W 168 joules. And we get delta U is equal to 0. Since I have said that it's coming back to the original state, so delta U is 0 here. And the first law is balanced. Okay, delta U is equal to Q plus W. So it is 0. Fine. So now coming to the and also this one delta H, it's one summation becomes 0 only. So delta H is also a state function kind of thing. Okay, it depends on the state. Unlike the heat and work here. So in the 5th question, we discuss in the above equation, if all the processes are irreversible with an efficiency of 80%, find Q and W. Okay. So generally, if it's a irreversible process, the efficiency is not 100%. So if we assume that like the step 1 was in the step 1, it was an adiabatic process. Right? Q is equal to 0. This is what we are understanding. But in reality, that Q is equal to 0 doesn't happen. And we can relate works. Okay. If it is a positive work, if like done on the system, then we have to work more. We have to give more work to make the same difference. That is why we say work irreversible is equal to work reversible by eta. Eta is equal to 0.8 here. And if it is negative work, if it's like done by the system, so like as if we are getting work from the system. Okay. So efficiency is less, 80%. It means it is giving lesser work. We want 100 work, but it is giving only 80 of the work. So that's how we define work irreversible is equal to eta into work reversible. Okay. So coming to the step 1, we had positive work. right? As you can see here, we had positive work here, 998 joules. And here also positive. Here it is negative, minus 1495 joules. So that's how I will find you. Here I can find work irreversible in the step 1. Okay, W1 I can say is going to be 1248 joules. Okay, now if this is there, now I can find the delta U is going to be same because it is a state process, depends on the state, right? So delta U is equal to Q plus W. So that's how you will get the Q equals to delta U minus W. So then you will get minus 250 joules. Okay. And if this is the step 1. If it is step 2, now you will get work irreversible is equal to similarly 665 by 0.8. So we will get 831 joule. Now again you will derive the QE. Okay, delta U and delta H won't change even if it is reversible or irreversible because they are not path function. Now you are defining Q, which is minus 1829 joules you will get. So, and in the step 3, you will get work is eta into work reversible. Okay, it will be lesser work because it is given by the system. So 0.8 into minus 1495, which is minus 1196 joules. Right? I'm writing slanted because there's space constraint. Okay. Excuse me for that. And now we have Q again similarly. Here delta U minus W. That's how you will get 1196 joule. Yes, sir.
Meet something?
Yes. Taking online class.
Don't come tell me you wanted to meet me. How long will this take? 5 minutes. Take it.
So we will have for the entire cycle, if we take now, if we sum up the heats, then you will have Q is equal to minus 883 joule. And work is 883 joule. So now overall, you can see in an irreversible process, we have Q. Q is minus 883 joules. And in reversible process, it is Q is equal to, as we have seen last time, it is minus 168 joules. Or I can say, talk about the work. Then I can say that this is around, okay, this is around 5 times of work reversible. So though we are saying the efficiency is of 80%, here we are getting 5 times the work. Like, sorry, positive, right? So we are doing 5 times the work which we have to do actually. So in the real system, you can say 80% efficiency is fine, right? But no, it is taking so much more energy as work we are doing, right? So that's what I wanted to conclude in using this question. And also, we have learned that how to calculate work and enthalpy differences and heat in different processes. So, thank you for today.